A single telescope measurement broke a rule planetary science had trusted for decades. A frozen moon orbiting Neptune, nearly 3 billion miles from the Sun, was suddenly behaving as if its climate had shifted in fast forward. And the worst part was this. The evidence appeared during a rare observation window that would vanish within minutes, leaving scientists almost no time to confirm whether one of the coldest worlds in the solar system had just invalidated everything they thought they knew about frozen planetary environments. The image itself looked simple, a distant pinpoint star hanging behind the black silhouette of Triton. Astronomers were watching what is called a stellar occultation. Normally, when an airless world moves in front of a star, the light disappears instantly, like switching off a lamp. But this time, the star did not vanish cleanly. It faded, slowly, gradually, almost as if something invisible was bending and scattering the light before it disappeared. That should not have happened, because Triton was not supposed to have much of an atmosphere at all. Less than a decade earlier, Voyager 2 had flown past Triton and delivered what scientists believed was the definitive answer. The moon was brutally cold. Surface temperatures dropped near minus 390 degrees Fahrenheit. Its thin nitrogen atmosphere barely existed, fragile enough that researchers assumed almost nothing on Triton could change quickly. That assumption had just started breaking apart. At first, the observations seemed routine. Occultation measurements were a standard method. Telescopes across Earth waited for these rare alignments because they could reveal pressure changes impossible to measure directly. The expectation was simple: confirm that Triton remained stable. Instead, the star kept fading too slowly. And that small delay changed the meaning of everything. Because gradual dimming meant the atmosphere surrounding Triton was thicker than expected, not slightly thicker. Nearly doubled. The object itself had not changed. The frozen moon still looked the same. The dark silhouette remained perfectly familiar. But now, that same image carried an entirely different meaning. Somewhere on that frozen surface, enough nitrogen ice had transformed into gas to dramatically expand an atmosphere scientists believed should barely move at all. Then, the safe explanation started falling apart. Maybe the instruments were wrong. That was the first hope. Ground-based observations are fragile. Atmospheric turbulence from Earth can distort measurements. Calibration errors happen. Timing mistakes happen. The star alignment itself could introduce noise. Researchers immediately began checking every possible failure point because the alternative was much worse. If the measurement was correct, Triton's climate was changing at speeds no one believed possible this far from the Sun. The same image returned. That tiny star fading behind a frozen world. Except now it meant something far more dangerous. Because if sunlight that weak could trigger atmospheric expansion this rapidly, then temperature stability across the outer solar system had been badly misunderstood. And suddenly, this was no longer just about Triton. Planetary scientists had spent decades building thermal models around a simple assumption. Distant icy worlds receive so little solar energy that environmental systems evolve slowly. Very slowly. Changes happen over centuries, not years. Frozen moons this far away were supposed to be predictable. But Triton had ignored that rule completely. Its nitrogen ice cap was reacting to seasonal sunlight in ways researchers had never modeled correctly. Even tiny increases in absorbed heat were enough to trigger large-scale sublimation. Solid nitrogen was turning directly into gas, thickening the atmosphere far faster than expected. The midpoint realization hit hard. This observation was not measuring a moon. It was exposing a failure inside planetary climate theory itself. And there was pressure. Because occultation opportunities are rare, Triton would not conveniently drift in front of another useful background star tomorrow. Astronomers had minutes to collect the cleanest possible data before the alignment disappeared. If they missed something now, confirmation could take years. Every second mattered. Again, the same visual returned. A tiny star behind a black frozen disk. The first time, it meant routine observation. The second time, it meant atmospheric thickening. Now it meant a scientific model collapsing in real time. Eventually, a new explanation emerged. Triton was experiencing seasonal solar forcing. Its orbit and orientation were slowly shifting enough that sunlight was warming nitrogen frost deposits concentrated on the surface. Even weak solar heating at extreme distances could destabilize the environment. And that introduced the real consequence. If Triton could reorganize its climate system this violently, with almost no solar energy, then scientists could no longer assume frozen worlds remain environmentally stable simply because they are cold. Entire planetary systems suddenly became less predictable. Distant moons, once categorized as static archives of ancient solar system history, were now active climate laboratories. Dynamic, unstable, vulnerable to rapid transformation. The final irony is impossible to ignore. Nothing dramatic happened on Triton itself. No explosion. No eruption. No visible storm. Just a single star, fading more slowly than expected. That tiny delay forced decades of scientific confidence to weaken overnight. And now, every frozen world in deep space carries a new question attached to it. Not whether it is frozen, but whether it is quietly changing faster than we ever imagined. Sometimes the danger is not what moves. It is what stayed still too long.